Hi, this is Dr. B.J. Swaraprasad, Professor of Civil Engineering, G. Pollard Engineering College, Kurnool. As part of series of video lectures on the course Design and Drawing of Hydraulic Structures, today I am going to explain the structure called tank sluice with tower head. Tank sluice with tower head. So in this particular video I am going to explain the design part of the tank sluice. Earlier videos related to the same course DDHS, the explanation of surplus wear, both design and drawing part of surplus wear has been completed. So now we will discuss the tank sluice with the tower head. So in this particular video, the entire design is divided into two parts. Part 1, design of ventway and sluice barrel. These two major components of the structure will be discussed. So first of all, let me explain about what is a tank sluice and also what is the tower head. You are all aware about the sluice. Sluice means an opening to be provided for a tank or any structure to draw water. Especially in water resources engineering, sluices are important components. Similarly, the tower head, which is a structure to be provided to regulate the flow through the sluice with shutter operating arrangements. Generally, we have some control on this flow. That's why to regulate the flow, it is required to provide a tower head for this structure. Coming to the design features or design components of this particular structure, so we have to estimate the discharge for the required sluice and a design of ventway and sluice, design of sluice barrel which consists of side walls and RC slab, and then design of tower head for which checking of the thickness of the well steening is most important, and finally cistern. These are the major components of the tank sluice. So see, this is a picture shows the actual sluice of a particular tank, village tank for minor irrigation. So this is the actual diagram. In another view of this sluice is like this. At the downstream side of the tank bund, we can see the sluice like this. So just these are some practical diagrams or pictures representing the tank sluice. Now coming to the problem statement, generally for design of any sluice, we have some data. We should have the data that is called input. So given data is like this. So to design a sluice taking off from a tank irrigating 200 hectares at 1000 duty. So this is the essential data required for the design of any sluice. Of course, the tank bund through which the sluice is taking off has a top width of 2 meters with standard side slopes of 2:1 side slopes. The other details are the top level of the bank has 40 meters level and ground level is at 34.5 meters, and also the hard soil for foundation is available at a level of plus 33.50. You can see clearly here how the elevations are right from the foundation level to the top of the bank. So it hardly 33.5 meters to 40 meters level. The sill of the sluice at offtake is 34 meters. This is also to be fixed. The sill level of the sluice should be at 34 meters. The maximum water level in the tank is up to plus 38 meters. The full tank level is plus 37 meters. And also the average low water level of the tank is 35 meters. So you can observe all these relative levels of the structure right from the bottom to top. So bottommost level is foundation level, that is 33.5 meters level. At the maximum highest level is plus 40 meters, that is the top of the bank level. Simultaneously, on the downstream of the tank bund, we have some canal. Regarding that canal also, the information required is bed level of the canal as 34 meters, FSL, that is full supply level of the canal as 34.5 meters, and bed width as 1.25 meters. Here also, in case of canal also, the side slopes are 1.5:1 with the top of the bank at 35.5 meters. This is the complete problem statement to design the tank sluice with tower head. So with this given data, now we will proceed the procedure of the design, step-by-step procedure. The first step of the design is estimation of the discharge. So the design discharge for the sluice. The sluice has to be designed for the particular discharge only. So for which as per the given data, I-cut area to be irrigated is 200 hectares. That means our sluice is going to irrigate 200 hectares of area. So for which the duty also given. If you are all aware about the duty. Duty is nothing but the area to be irrigated if 1 cubic of water is continuously supplied throughout the crop period. As per the standard definition, we have duty like that. In the present case, duty is given as 1000 hectare per cubic. Accordingly, we can calculate the discharge required for a given sluice as Q is equal to area by duty. A simple formula it is, from which you will get the discharge for the sluice as 0.2 cubics only, 0.2 meter cube per second. So with this design discharge, now we have to design the ventway and also sluice. These two components are simultaneously to be designed. So first of all, let me explain what is ventway and what is sluice. So before going to design these two components, so we should know what is sluice and what is ventway. As already said, the sluice is nothing but the opening to be provided for a bank of a tank. So similarly, ventway is also in the similar meaning. It is also a opening in excess of flow area for other works or other purposes like repairs, etc. So in general, most of the cases, the ventway is of a standard size, certain 2 feet by 2.5 feet size, that are 60 centimeter by 75 centimeter size. So such that we can work some repairs, etc. through that opening. So within this ventway, we have to provide the sluice. See here how to design the ventway and sluice accordingly. The area of the ventway of the sluice must be such that it can draw normal supplies of water when the tank is at the low water level. Even though the water level in the tank is at low, we have to draw the water from the tank. Accordingly, we have to design the sluice. In the present problem, the average low water level of the tank is given as plus 35 meters. We have to observe these relative levels. It is most important. So in this case, if you see, the average low water level is given as plus 35 meters, whereas the sill level of the sluice at offtake is given as 34 meters. That means there is 1 meter head of water is available. The head of water available above the sill level of the sluice for drawing supplies is 35 minus 34, that is 1 meter. However, the sluice opening is designed to draw the normal requirements with the driving head of certain limited value, that is 0.25 meter, and when the tank water level is high, the ventway is throttled by means of screw gearing shutters. This concept is also often required for most of the sluice designs. So in this case also, though we have 1 meter head of water available, but we are not supposed to utilize that entire 1 meter head of water. To supply 0.2 cubics of discharge through a particular sluice, it is required a minimum driving head of 0.25. You can see how this 0.25 is arrived. It is sufficient to supply water of 0.2 cubics of water. Therefore, by assuming the driving head of 0.5 meters above the center of the opening, the area of the opening, that is ventway, is given by the following formula. So this is a very simple formula, discharge formula or orifice formula. You are all aware about discharge through a orifice. So whatever the shape of the orifice may be, whether it is circular or any other, a simple equation for discharge through a orifice is given by Q is equal to CD into A into root 2 GH. This is from the continuity equation. As continuity equation is given by Q is equal to area into velocity, similar way we have this equation. CD the coefficient of discharge of a large orifice. So large orifice and small orifice, again we can differentiate. Most of the irrigation tanks, the orifices or the sluices comes under large orifice category only. That's why you have to adopt the suitable value of CD as 0.6 for large orifice. Area is of course the area of the opening or area of the flow passage, and root 2GH represent the theoretical velocity. So that's why the final equation for discharge is given by Q is equal to CD into A into root 2GH. You know all the terms. CD is the coefficient of discharge, A is the area of the ventway to be provided, H is the driving head to be assumed, and discharge Q is the discharge 0.2 Qmax already we calculated. Accordingly, from this except A, all other terms we know, such that we can calculate the area of the ventway or area of the opening as A is equal to 0.151 square meters. So this area approximately gives a diameter of 0.45 meter, that is 45 centimeters circular opening. So pi by 4 d square. Suppose if you consider the area of a circular opening of size 0.45 meters, so it will be approximately equal to 0.15 square meters. So therefore we can arrive this size of the circular opening as 45 centimeters with the calculated value of A. Generally, the maximum size of the ventway to be adopted for the sluice barrel is about 75 centimeters by 60 centimeters. That's what I already told. The standard size of the ventway should be 75 centimeters by 60 centimeters. That means 60 centimeters as the width and 75 centimeters as the height, so as to allow for repairs and etc. So actual our area required is 0.45 centimeter diameter circular hole only, but we are providing the ventway of size 60 centimeter by 75 centimeters. Therefore we have to insert a diaphragm stone with a circular opening of 45 centimeter diameter in it. As shown in this figure, here you can see in this figure the circular opening of size 0.45 meters or 45 centimeters, whereas the ventway is 60 centimeter by 75 centimeters or 0.6 meter by 0.75 meter. So what we have to do is we should provide that ventway of the same size, and also at the entrance of the sluice barrel we have to insert such type of stone that is called diaphragm stone with a circular hole of 45 centimeter diameter, such that we can allow the water through this ventway restricted to the circular opening of 0.45 meter only. See, this diagram will give the complete details about the relative levels, various levels of the tank and tank sluice, as our aim is to design the tank sluice, so the sluice of the tank. So this figure shows the cross-sectional view of the tank bund. The clear details are given here. So top width is 2 meters at a level of plus 40 meters. That was given in the problem. Similarly, various water surface levels you can see right from top to bottom or bottom to top. So let us consider from bottom. So the foundation level, hot soil is available at plus 33.5 meters as given in the problem. That is to be taken as the reference, that is bottommost level of the structure. And the sill of the sluice, the sill level, you are all aware, sill level means the level above which water is flowing. The sill level of the sluice has to be kept at plus 34 meters. It is also clearly mentioned. Whereas the existing ground level is at about plus 34.5 meters. So every half an hour, half a meter difference, we have the various positions. Foundation level is at plus 33.5, sill level is at plus 44 meters, whereas the existing ground level is plus 34.5 meters. Now coming to the tank, the entire height of the tank bund is nearly 5.5 meters. 40 minus 34, here from 40 to 34.5, that difference is 5.5 meters. That means the height of the tank bund is 5.5 meters, within which the maximum water level is at plus 38 meters, the full tank level is plus 37 meters, and low water level is at plus 35 meters. So these are the various levels or relative levels within the tank. So our design is to provide the sluice to the tank bund. So in this figure, it is very clear that this is the ventway by the side of which I have mentioned the circular opening as the sluice. I hope it is clear. The ventway, sluice and also tank bund. With all the relative levels and dimensions, it is clear. By the side of this tank bund, we can also see the cross section of the channel for which the water is to be supplied. This data is also given in the problem. The bed width of the channel as 1.25 meters as well as FSL is plus 34.5 meters and side slopes of 1.5:1. At the top of the canal is plus 35.5 meters. These are all given in the existing problem. Now coming to the sluice barrel. So after fixing the ventway size and also size of the sluice, now we have to design the sluice barrel. Sluice barrel in the sense the longitudinal view of the sluice, the longitudinal structure. So throughout the width of the tank bund, you can see earlier diagram from upstream side to downstream side or inside the tank to outside the tank. So completely this barrel should be provided. So that is called sluice barrel. Now and then we are going to use that word sluice barrel. That means the structure to be provided from the upstream side of the tank bund, tank to downstream side or inside the tank to outside the tank. See here the position of the sluice barrel. The sluice barrel is buried under the tank bund at an appropriate level. The barrel will have the masonry side walls. Generally, in general, these barrels are to be constructed like that. 2 side walls, bottom flooring and top roof slab. These are the 4 components of the sluice barrel. While designing the sluice barrel, we have to design all these 4 components and also we have to check the stability of side walls. So we will proceed the procedure. So generally the roof can be either RC slab laid in situ or precast RC slabs with a leveling course of concrete laid over it. Both ways we can provide this sluice barrel. One is the roof slab. The roof slab may be either cast in situ or precast RC slabs. And the foundation of the 2 side walls is continuous in concrete with 60 centimeters thick with a wearing coat of richer concrete of 10 centimeter thickness serving as the floor for the barrel in between the side walls. So let us imagine, I will show the figure diagram also. See here. See this diagram in which it is clearly mentioned the ventway of size 0.6 meter by 0.75 meter. That ventway is surrounded by 2 side walls, masonry side walls and also bottom foundation concrete, top roof slab. So 2 side walls and bottom foundation and also top roof slab. So these are the 4 major components of this sluice barrel. As it is the sluice barrel, see here the foundation of the 2 side walls, the continuous foundation, combined footing can be provided. The foundation for the 2 side walls is continuous in concrete and a minimum thickness of 60 centimeter with a wearing coat of richer concrete of 10 centimeters within that 60 centimeters only, serving as the floor for the barrel between the 2 side walls. So this diagram represents a cross-sectional view of the sluice barrel. Now we are talking about the sluice barrel. This is the sectional view of the sluice barrel. Right. Let us consider the design of RC slab, that is roof slab for sluice barrel. The RC slab of the sluice barrel is designed for the clear span of 60 centimeters supporting on overburden. So generally above since this sluice barrel is buried under the tank bund, so at the top of the sluice barrel huge amount of earth is present. So therefore the overburden pressure, the weight of the earth over the sluice barrel is the important force acting on the structure. So accordingly we have to design the slab for the roof slab for the sluice barrel. So the clear span is 60 centimeter as you observed in the previous diagram. the clear span for this roof slab is in between the two side walls, which is only 0.6 meters, 2 feet width only. So therefore the clear span for this slab is only 0.6 meters. So for which you have to design the slab. So designing for the maximum possible load, considering the section of the barrel at the center of the bank, the height of the earth supported by the slab is 5.1 meters. This 5.1 is, again you can see, this top level of the bank is 34.9. If you see in this figure, the top level of the sluice barrel is, including the roof slab, 34.9, whereas the tank bund top level is 40 meters. That 40 minus 34.9 is nothing but 5.1. So that means 5.1 meters of depth or thickness of the earth is present on the sluice barrel. Accordingly, we have to design the roof slab. I hope it is clear. Designing for the maximum possible load, considering the section of the barrel at the center of the bank, the height of the earth supported by the slab is 5.1 meter. A typical cross section, or a critical cross section to be considered as at the center only. Center of the bank, if you consider the sluice barrel, for which the height of the earth resting on the slab is maximum, that is 5.1. The earth will be charged with the percolating water through the embankment, hence it is designed for saturated earth fill. So that earth is, since we are assuming that always water will be present in the tank, so therefore the soil within the tank bund is the saturated soil only. So therefore we have to design for saturated earth fill. The slab has to be designed for the load of saturated earth fill. Accordingly, the weight of the saturated earth is 2240 kg per meter cube, that is the unit weight of saturated earth. Similarly, unit weight of concrete also you are all aware, that is 2400 kg per meter cube. So these unit weights of different materials you should know, so concrete, soil, masonry, etc. So it is all to be used in our design, unit weights per cubic meter. So first of all, initially assume the thickness of the slab as 0.15 meter, that is 15 centimeter thickness of the slab is to be assumed. So only thing here what we are doing is, as part of the design of the slab, first we have to assume certain thickness of the slab, that is say 15 centimeters, and then we should check this thickness is sufficient or not as per the loads acting on the slab, whether the thickness is sufficient or not. That's what we have to check. So from the given data of the problem, sill level of the sluice is plus 34 meters, top level of the ventiway is plus 34.75. As the height of the ventiway is 0.75, that is 34.75 is the top level of the ventiway. So similarly, the top level of the RC slab is 34.90. Again, we are going to add 0.15 meters, as thickness assumed is 15 centimeters. 34.75 plus 0.15, which is equal to 34.9. This would be the top level of the RC slab. Similarly, the top level of the bank, tank bund top level already given as 40 meters. So again you have to consider all these relative levels, 34 meters, 34.75 meters, 34.9 meters and 40 meters. Accordingly, we have to consider the weights. So therefore, the height of the bank over the barrel is 40 minus 34.9, which is equal to 5.1 meters. That's why we considered earlier also the height of the earth over the barrel is 5.1 meters. Now, as a clear span is 0.6 meters, the effective span of the slab is equal to 0.6 plus 0.15. On both sides certain bearing is required, that is to be considered as 0.15. Therefore, the effective length of the effective span of this slab as 0.75 meters. See here. In this diagram, you can clearly observe all the dimensions. The foundation concrete of 60 centimeters thick. Let us assume two masonry walls. These are the two masonry walls. This is one masonry wall. This is another masonry wall. Two walls. And In between the ventway is there. This is the opening of 60 centimeter by 75 centimeter height, and on which the roof slab of 15 centimeters thickness we assumed. Slab is to be provided like this. So its bearing is also both sides a certain bearing on this masonry walls. So accordingly, finally the top level of the roof slab is at plus 34.90 meters. Now, for the design of the slab, as usual, we have to consider unit length, 1 meter length of the slab. Whatever the length of the barrel may be, we have to design for unit length of the slab only, 1 meter length. Accordingly, the self weight of the slab per meter length is given like this. So, you are all aware the weight or a force is given by the unit weight multiplied with the volume. Simple logic, the volume of the component multiplied with the unit weight of that material, that will give the weight of the component. So here first you consider the self weight of the slab itself, RC slab self weight. The unit weight of the concrete is 2400 kg per meter cube, and the volume of slab per meter length is given by 1 meter by 0.7 meter by 0.15 meter. That will give the volume. 1 into 0.7 into 0.15 will give the volume of the slab. Multiply with the unit weight of the slab concrete, that is 2400, which will give 270 kgs. This 270 kgs is what? This 270 kgs, it is weight of the slab per meter length. Of the standard weight per meter length, the weight is 270 kgs. Similarly, the weight of the saturated earth above the slab, this is the major external force acting on the slab. Self weight is simply 270 kgs only, whereas the weight of the overburden pressure, that is weight of the saturated earth on the slab, having a height of 5.1 meters. That's why it becomes 8,568 kgs. That is arrived simply by multiplying the volume with unit weight. Again, unit weight of saturated earth is assumed as 2240 kg per meter cube, and volume of the earth resting on the slab is 1 meter into 0.75 into 5.1. All these three dimensions are length, width and thickness or height. Accordingly, you will get the weight of the earth on the slab as 8,568 kgs. Therefore, the total load including self weight of the slab is equal to 270 plus 8,568, which is equal to 8,838, nearly equal to 8,850 kgs per meter. So this is the total load on the slab for our design purpose per meter length. Always you should remember this, these values are per meter length of the slab only. Now, then in the next step, you have to calculate the maximum bending moment. So, for simply supported slab, the maximum bending moment is given by WL by 8. So, already the total weight is calculated as 8,850, and length L means effective length is 0.75 meters divided by 8. WL by 8, which is equal to 829, approximately 830 kg meters. That is the moment, maximum bending moment, 830 kg meters. We can convert into kg centimeters also. 82,960 kg centimeters is the maximum bending moment of the slab. And also, generally for all of our hydraulic structures, the most of the cases the concrete to be used as M20 grade, approximately the mixed proportion as 1:2:4 cement concrete. With the usual stresses, the compressive stress is 52.5 kg per centimeter square, as well as tensile stress is 1260 kg per centimeter square. For this 1:4 concrete, these are the permissible compressive stresses, compressive stress as well as the tensile stress of the concrete. And also M is the modular ratio, it is 15. The effective depth of the span is given by that formula, usual formula, standard formula we are going to use to determine the effective depth of the slab. M is equal to QBD square. So by using all these relevant values, you will get the effective depth D as 9.7 centimeters. And then adopting the clear cover of 2 centimeters as per standards, it is enough to adopt the overall depth of the slab as 12 centimeters. So the effective depth calculator is approximately 10 centimeters, with a clear cover of 2 centimeters. So the total, that is overall depth of the slab, becomes 12 centimeters only. However, we already provided 15 centimeters depth of the slab, thickness of the slab, which is greater than the required depth. Hence, we can adopt the same thickness as the thickness of the slab. So here only what we have done, just simply we assumed certain thickness of the slab, and then we checked that against the various possible forces or loads acting on the slab, whether the assumed thickness is sufficient or not. That's what we checked here. So in the present case, the required thickness of the slab is 12 centimeters only, whereas we provided 15 centimeter thickness of the slab. Hence it is okay. Now coming to the side walls. So the design of the slab, roof slab, is over. Now coming to design of side walls. In here the design, in the sense not in-depth design, just you have to assume the dimensions of the side wall as per the practice and as per the experience. And only thing is we have to check the stability of side walls against the various possible forces. That's all. So that's why we can also consider it as the stability analysis of side walls, not the design of side wall. So side wall only we have to assume the thickness and the dimensions of the side walls. As already mentioned, if you see the previous diagram, it is very clear that the trapezoidal shaped side wall, this is the side wall of the trapezoidal shape, having certain top width, bottom width, and the sloping side, vertical side, etc. Similarly, another side wall, two side walls we have. So we have to check the stability of one of the side walls. The side walls act like abutments for the ventway. These side walls will act as a abutment, supporting structures. They take the side thrust, the horizontal earth pressure, due to lateral earth pressure and also superincumbent weight of the surcharged earth standing directly on the wall and the roof slab. So it is very clearly shown in the figure also. To design the side walls, we have to assume the suitable size of the side wall in such a way that should withstand the lateral earth pressure, which is acting horizontally on the wall, and also superincumbent weight of the saturated earth, which is acting at the top of the wall, both in the vertical direction as well as horizontal direction. The forces are acting. So stability analysis of the side wall. Now we will take up the stability analysis of the side wall. The stability of one side wall is checked by assuming the section as shown in figure. See here. It is very clear that all the possible forces acting on the side wall. So for our convenience, we considered all the forces into number of component forces. For easy to calculate, for calculation purpose, we have to consider the various possible forces acting on the side wall as the component forces, instead of taking only two number of forces. Actually, there are only two forces acting on the side wall. They are, one is self weight of the wall, obviously. Second one is the external force. External force is due to presence of earth. The side wall is completely covered with tank bund, so therefore at the top and side earth will be there. So therefore this earth, standing earth, will exert certain pressure on the wall. That pressure force also to be considered as external force. Okay, there are only two forces. One is self weight of the side wall. Second one is the earth pressures, whether it may be horizontal or vertical earth pressures. These are all to be calculated as the various forces acting on the wall. This is very important for the stability analysis of any structure. So generally what we are doing in the stability analysis, so first we have to identify the various forces acting on the structure, and then determination of magnitude, direction and position of all the forces, and then moment of all forces about the two, and then check the stresses induced, stresses developed within the structure, whether they are within the permissible limit or not. That's what stability analysis says. Here also we are doing the same thing. So for that purpose, we have to consider a typical section of the side wall. See here, let me explain about this diagram first. So first, if you understand this diagram, then we can easily calculate all necessary calculations for the stability analysis. So let us consider this is this hatched portion. This portion represent the side wall of one of the side walls of the sluice barrel. So one face of this wall is vertical, inner face is vertical, whereas outer face is sloping one. Outer face is sloping one. Is it clear? So therefore, it is a trapezoidal in shape. Trapezoidal cross-sectional side wall is assumed. Let us consider the dimensions of this side wall as top width is 0.45 meters and bottom width as 1 meter. So just by experience and practice only we can assume like that. And of course the height of the wall, you are all already known to you. The height is just the height of the ventway, which is 0.75 meters plus inclusive thickness. Thickness of the slab as 15 centimeters. Therefore 75 plus 15, total 90 centimeters is the height of the wall required. 0.9 meters. You can see here also the relative levels, plus 34 meters plus 34.9 meters. So that's why the height of the wall is nothing but 34.9 minus 34, which is equal to 0.9 meters. It is clear that the dimensions of the trapezoidal cross-sectional masonry side wall are 0.45 meters top width, 1 meter bottom width, with inner side vertical and outer side is sloping, having the height of 0.9 meters. These are the dimensions of the side walls. Now we are going to consider the various possible forces acting on this side wall, including self-weight. You see in this diagram, number of component forces are there. Let us consider 1, 2, 3, 4 like that, suffix P1, P2, P3, P4, P5, etc. You see there are total 5 vertical forces. All these vertical forces, if you observe in the figure, they are acting vertically downward. As shown in this diagram, all these forces, vertical forces, and also their directions are vertically downward. Whereas only one horizontal force, that is H, due to lateral earth pressure. So this is also to be considered. One of the important force acting on the wall is horizontal thrust due to lateral earth pressure. Let it be H. So finally, how many number of forces here? We have 5 number of vertical forces. All are acting vertically downward, including self-weight. The P5 represents the self-weight. And also only one horizontal force, that is H, due to lateral earth pressure acting towards the wall. So these are the forces to be considered. I hope it is clear. And also along with these dimensions of the side wall, we should observe the surroundings also. Surrounding of the side wall. The side wall is completely covered with tank bund. That means it is covered by the earth fill. That is saturated earth, for which already you know we assumed that the saturated unit weight of saturated earth 2240 kg per meter cube. 1 cubic meter of saturated earth weighs 2240 kgs. That much weight or that much force is acting on the side wall. Only thing is, this total vertical force is divided into number of components like P1, P2, P3, P4, etc. That's all. Whereas the only horizontal force is H, that is to be calculated using the Rankine's formula. The next slides we will discuss. So as explained earlier, these are the various possible forces. Let me explain one by one. The first one is lateral earth pressure. This is the most important external force acting on the side wall. Okay. The horizontal or lateral earth pressure acting on the wall is calculated by Rankine's theory. I think you are all aware about the Rankine's theory in the soil mechanics, Rankine's formula, Rankine's theory to obtain the intensity of earth pressures. So the intensity of earth pressure at the bottom and the top of the wall are given by the formula P is equal to, you refer this formula, P is equal to gamma H into 1 minus sin theta by 1 plus sin theta, in which first of all you should know all the terms involved in this equation. What is P, what is gamma, what is H, and what is theta. So P is the intensity of earth pressure. You remember P is the intensity of earth pressure, whereas gamma is the unit weight of the material. That material is earth, saturated earth. That value is also already assumed as 2240 kg per meter cube. H is the height, wherever you required from the top. So at a depth of H, you want to know the earth pressure intensity, that will be given by P is equal to gamma H into 1 minus sin theta by 1 plus sin theta is the constant as per the Rankine's formula, in which theta is the angle of repose. So this theta value generally for most of the soils to be assumed as 30 degrees. That theta is nothing but angle of repose. In the present case, we have to assume the theta value as 30 degrees. So therefore, using this equation, we can calculate the earth pressures at top and bottom of the wall. See here, in this figure, top, let it be point D, and bottom, the point A. At these 2 points, so what is the intensity of earth pressure acting? That's what we have to determine. Okay. See, these are the calculations involved to determine the earth pressure. By using the same above equation, that is P is equal to gamma H into 1 minus sin theta by 1 plus sin theta, the corresponding values has to be substituted in that equation to get the earth pressure intensities. First one is earth pressure at A. Again, you refer this figure. A is nothing but the bottom of the wall, bottommost corner of the wall. External bottom corner of the wall is A. Similarly, external top corner of the wall is D, A and D. As the external face of this wall is subjected to lateral earth pressure, we have to calculate the intensity of earth pressures at bottom A and top D of the wall. So those values are like this. Simple substitution only. 2240 is the gamma value, that is unit weight of the saturated earth. Multiply with the corresponding height at A from the top of the bank. If you see, from the top of the bank is 40 meters, bottom is 34, bottom of the wall is 34. So 40 minus 34 is equal to 6. That's why here we used the value 6 for point A. If you want, you can see the top of the bank. Here this is the top of the bank. This is at 40 meters level. Point A is at the bottom of the wall. From this top of the bank to bottom of the wall, the difference is 40 minus 34, which is equal to 6 meters. So that's why here we have taken the 6 meters as H. So 1 minus sin 30 is 0.5. Similarly, 1 plus 0.5. As sin 30 is equal to 0.5, directly I substituted the values here, from which we got the earth pressure at A as 4480 kg per meter square. This is the earth pressure at A. That means at the bottom of the wall, bottom of the side wall, the earth pressure value is intensity is like this. The similar way you can calculate the earth pressure at D, that is at top. That is also given by the same equation. Only thing is just you observe the difference. Here the depth at the top minus 0.9. So that's why it is 5.1. 6 at the bottom of the wall, the H is equal to 6, whereas at the top of the wall, the H is equal to 5.1. If you want, you can see. So 40 minus 34.9. This 40 minus 34.9 is equal to 5.9. So that's why here 5.1. That's why here we consider the 5.1. The remaining all the same. Accordingly, we will get the value, that is intensity of earth pressure, as 3808 kg per meter square. Is it clear? Both are the intensity of pressures at the top and bottom of the wall. Now, the total magnitude of the earth pressure, ultimately what we required the lateral earth pressure H. That is obtained simply from the area of the pressure distribution diagram. So if you have the area of pressure distribution diagram, first by knowing the intensity of pressures, we can calculate the area of that diagram, that is simply a trapezium. So therefore, the area of the trapezium with appropriate intensity of earth pressures as the ordinates, you will get the total area, which is equal to, as calculated here, the intensity at the top, intensity of the bottom, and divided by 2, average intensity average intensity multiply with this height of the wall. This 0.9 is the height of the wall. This is average intensity of earth pressure. So which will give 3730 kg per meter. You see here 3730 kg per meter is the total horizontal force, that is lateral earth pressure per meter length, whatever the length of the barrel may be. And then it gives the magnitude only. Now what about the direction? Direction is horizontal, no doubt about it, and its position, where exactly it is acting. So for all these forces, subsequently we require their lever arms also, as we have to check the stability against the moments also. So therefore their lever arms also to be known. So for that, for this particular force, lateral earth pressure, its distance is just centroid of the trapezium. This is the formula of centroid of the trapezium, with which you will get the 0.44 meter above the point A. This is the distance where this lateral earth pressure is acting. The 0.44 meter is the distance from the moment center to the line of action of the force. Again you can refer this same. See here, this H is the horizontal force. This just now we calculated from the area of the pressure distribution diagram, and it acts at a distance of, suppose from the bottom, this bottommost corner is known as toe. Bottommost corner, inner corner of the structure is called toe. So next we are going to take the moments about this toe. So for taking the moments, we require forces and their perpendicular distances. So say for example, if you want to determine the moment of this force, horizontal force H about toe, what we require? We require the perpendicular distance of this horizontal force. This is obtained as 44 centimeters. See here, this is 0.44 meters above the point A, that is from the bottom of the wall. This is the calculation of lateral earth pressure, which is the major external force acting on the wall. Next, coming to the other components, let us consider the next component. Remaining components are all the weights only, weight of the earth only, and they are acting vertically downward direction. There is no doubt about it, as all these are acting vertically downward, right? Only thing is we need to calculate the magnitudes only. That too, magnitude of the earth pressure or earth force. That means simply weight of the earth or weight of the slab, etc. Only weights are to be considered as the vertical forces. And you remember, all the forces are acting vertically downward. Let us consider one by one. This is a weight of the roof slab transmitted to the wall. Always we have to refer this figure only. See here, what is P1? P1 is, here it is mentioned as P1. This P1 is weight of the slab with the weight of the earth on the resting on the slab to be transmitted to each wall. As the slab is resting on both the walls, whatever the weight of the earth resting on the slab, including the self weight of the slab, that will be transmitted equally to both the walls, as the slab is resting on the side walls. So therefore, straight away we can take the 50% of the total weight of the slab and its weight above the slab as the weight transmitted to the side wall. It is very clearly shown in this figure that whatever the weight of the slab and earth above the slab, that will be transmitted to both the walls, both the side walls, 50%. So therefore, here we can see weight of the roof slab coming on each side wall, P1 is equal to 8850 divided by 2. That 8850 is the total weight of the slab inclusive of earth resting on the slab. I will repeat once again. That 8850 is nothing but the total weight of the slab inclusive of the weight of the earth resting on the slab. So that is 8850. Already we calculated while designing this slab. So that total weight is equally distributed to both the walls. That's why 50%, half of that weight is to be taken as 4425 kgs. This is the value of weight of the roof slab transmitted to the wall. Okay, and also Next, immediately its position, where it is acting. This acts vertically on the side wall at the distance of 7.5 centimeters from vertical face. Again, we can see in the figure, see, P1 is acting vertically downward and its lever arm distance with respect to the vertical face of the wall or with respect to this toe is, as this bearing is 15 centimeters, it is mentioned as 15 centimeters. Half of this 15 divided by 2, 7.5. So you can see this 7.5 is the lever arm. So this 50% of load transmitted to the wall is acting at a distance of 7.5 centimeters from the vertical face of the abutment. Okay, next, coming to the next component, let it be P2. What is P2? Weight of the earth on the top side of the wall beyond the slab, P2. You have to observe carefully. I will show. P2 mentioned here. So P2 is the weight of the earth resting on the wall, top of the wall, beyond the slab. As the top width of the wall is 0.45 meters, out of which 15 centimeters is the bearing of the slab. So therefore, the remaining width 45 minus 15, total 30 centimeters, remaining 0.3 meters. This beyond slab means top width of the slab, beyond the slab means 0.45 meters, 0.15 meters, that is 0.3 meters. Now, we have to consider the weight of the earth resting on the top of the wall up to the tank bund. This is to be considered as P2. It is clearly mentioned in this diagram. P2 is nothing but weight of the earth resting on the top of the wall beyond the slab. How to calculate this value? See here. P2. See the details, it is very clearly mentioned. The top width of the side wall is 45 centimeters. Okay, we have to deduce the slab bearing, that is 15 centimeters. The portion of the masonry wall remaining is 45 minus 15, that is 30 centimeters. Therefore, the weight of the earth coming down on this portion is P2. As usual, the volume 1 meter length and 0.3 meter width, 5.1 meter height. This is the volume of the earth above the wall. Multiply with the unit weight of the saturated earth, that is 2240. So which is equal to 3427 kgs. So like that we can calculate this component also. Similarly, where it is acting, this weight acts vertically on the side wall at a distance of, again you refer for lever arm or distance of this force. Say this P2 is acting, where it is acting in vertically downward direction with respect to this toe, with respect to this vertical face of the wall. The line of action of this P2 is at a distance of this 15 centimeters plus 30 divided by 2. Okay, so therefore it is 0.3 meters. See here, 15 centimeters is the bearing of the slab plus half of the 30, half of the remaining width, 30 centimeters. So in total in centimeters, 15 plus 30 by 2, again it is 30 centimeters from the vertical face of the abutment. You see, from this vertical face 15 centimeters plus this 30 divided by 2. So totally it is acting at a distance of 0.3 meters, that is 30 centimeters from the vertical face or toe of the abutment. Okay. Next, the weight of the earth standing on the sloping side of the wall, let it be P3 and P4. Two more components. See here, this is our sloping side of the wall. On the sloping side also earth is there. Earth is resting on the sloping side. This again, this will be divided into two components, P3 and P4. As shown in this figure, P3 and P4. P3 the weight of the earth corresponding to this rectangular portion, whereas P4 is the weight of the earth corresponding to this triangular portion. So on this sloping side, the entire earth is there from bottom to top. So that is divided into two components again for our convenient only, P3 and P4. Accordingly, by using the same procedure, we can calculate the magnitudes of P3s and P3 and P4 as, see, this can be split into two vertical forces P3 and P4. Let us consider the first one, the force corresponding to the rectangular portion. The dimensions are very clear, 1 meter length, 0.55 meter width, that is bottom width, sloping width, and 5.1 meter is the height. Multiply with the unit weight of earth, it will give some value, 6,283 kgs. It's a centroid, which is acting vertically at a distance of 45 plus 55 by 2, which is equal to 72.5 centimeters from the vertical face. Similarly, the other component P4 corresponding to the triangular portion. One is rectangular portion, another one is triangular portion. So as shown in this figure, P3 is corresponding to rectangular portion, P4 is corresponding to triangular portion. Their magnitudes and their lever arms from the you remember all the distances should be calculated from this moment center, that is toe only. Right. So like that we will get the magnitudes and their positions. And finally, the weight of the masonry side wall, that is self weight of the wall. As I already mentioned, it is the masonry wall. The material used is stone masonry. So for which we have to assume the unit weight. The unit weight of the masonry is 2100 kg per cubic meter. So therefore, we can easily calculate the total weight of the masonry wall. As we know the dimensions of the wall, so 0.45 meter at the top, 1 meter at the bottom, trapezoidal cross section. Therefore, with a height of 0.9 meters, you will get the volume as that expression. Multiply with 2100, you will get the total weight of the masonry wall, which is acting at a distance of 0.39 meters from the vertical face. So after calculating all the forces and their magnitude, directions and positions, now we need to calculate the moments of all the forces. As part of stability analysis, you are all aware. Just to recall the procedure of stability analysis. First we have to identify the various forces acting on the structure, then magnitude, direction and positions of all the forces, and then take the moments of all the forces about the required point, that is toe or moment center, whatever it may be, and then you have to observe certain salient values. See, this table will give whatever the calculations you have done so far in a single statement, single table. It is very clear that P1, P2, P3, P4, P5 all are vertically downward forces. They are weights only. Only horizontal force is H. Towards right hand side it is acting. Their magnitudes already calculated above, and their lever arms also observed like that in centimeters. Therefore, the moments of all forces about toe are given like that, in which if you see the only moment, that is clockwise moment or negative moment, is due to horizontal earth pressure. Again you can see all the vertical forces are acting downward. Therefore, with respect to toe, if you take moments of all the forces, they are anti-clockwise moments. Let it be positive. The only moment due to horizontal force about toe is clockwise. So therefore, it is negative. So accordingly, we have to consider the sign convention also. See here, this is the magnitude of horizontal force. Its lever arm, which is acting at a distance of 44 centimeters from the toe. Therefore, 1,64,120 kg centimeters is the moment, that is negative moment or clockwise moment, whereas all other moments are positive moments. So therefore, finally for the stability analysis, we required the sigma V, that is sum of all vertical forces, and sigma M, that is algebraic sum of all moments, whether it is positive or negative. So algebraic sum of all the moments as sigma M. And of course, eccentricity, this is the cross section of the side wall, you see, in which after calculating horizontal forces and vertical forces, we can observe the resultant where it exactly acts. So this is the standard procedure to determine the eccentricity and accordingly the normal stresses. So say the distance of the resultant from the toe is given by sigma m by sigma v. Okay, that is in the present case it is 33 centimeters. We got 33 centimeters as the lever arm for the resultant force. So therefore, the eccentricity E is given by half of the bed width or bottom width of the wall, that is 100 centimeter. 1 meter we assumed. 100 by 2 minus B by 2 minus X bar. This is the formula for eccentricity. For any structure, the eccentricity is given by like this. So B by 2 minus X bar, where X bar is given by sigma m by sigma v. So accordingly, in the present case, we got 17 centimeters as the eccentricity. As shown in this figure, it is very clear that in this figure, B by 2 is the half of the bed width, bottom width. X bar is the distance of line of action of this resultant from the toe. This is toe. And E is the eccentricity from the center. So accordingly, we got nearly 17 centimeters as the eccentricity. For stability purpose, the allowable eccentricity is always B by 6. E should be B by 6, less than B by 6, less than or equal to B by 6. So therefore, the allowable eccentricity is 16.7 centimeters, whereas in the present case, it is around 17 centimeters. So the resultant is just outside the middle third. Of course, it is recommended, not much deferred. So it is just outside the middle third. In the last step, we need to calculate the normal stresses also. Vertical normal stresses at the toe and the heel of the wall. As part of the stability analysis of the side wall, this is the cross section of the side wall. At the bottom inner corner is toe and bottom outer corner is heel. At these 2 points, we have to check the normal stresses. You are all aware the normal stress is given by this standard formula. Pn is equal to sigma v by A into 1 plus or minus 6E by B. So this is the standard formula to be used to determine the normal stresses, in which all the terms also you know. E is the eccentricity, B is the bed width or base width, sigma v is the algebraic sum of all vertical forces, and A is the cross-sectional area. So accordingly, plus or minus in this equation, if you observe, if you take positive sign, that will give the normal stress at toe, and similarly if you take the negative sign, it will give the normal stress at heel. That is only the difference, whereas the entire expression is the same, only plus or minus only. First, let us consider the maximum compressive stress at toe. If you take positive sign in this equation, it will give the compressive stress at toe. That will be 32,441 kg per meter square. Since we substituted all in meters, so the compressive stress is 32,441 kg per meter square. Whether it is within the permissible limit or not, that's what you have to check. See here, that this 32,441 kg per meter square, if you convert into kg per centimeter square, conveniently it is 3.24 kg per centimeter square. So what is the permissible value? It is 9 kg per centimeter square is the permissible limit. So hence our design is safe, as the maximum compressive stress at toe is obtained as 3.24 only, whereas the permissible limit is 9 kg per centimeter square. Hence it is okay. Similarly, tensile stress at heel also, see, with the negative sign, if you take sigma v into 1 minus 6E by B, you will get negative value, minus 321 kg per meter square, or that is 0.032 kg per centimeter square. So this negative sign indicates tensile. In default, the stresses should be compressive. If you got negative sign, that indicates tensile stress. However, this tensile stress also should be within the permissible limit. There are certain permissible values. The maximum allowable tensile stress for masonry is, this is as per code, we have this value 1.25. Our obtained value is 0.032 only. It is far less than 1.25. Hence the section assumed is safe and can be adopted. So this is about stability analysis of side wall of the sluice barrel. So in this lecture, we covered two major components of the structure. One is design of ventway with sluice. Second one is design of sluice barrel inclusive of stability analysis. The remaining part of the design will continue in the next video. Thank you.